Hernan said, my name is Jeff Bonkoski, and to give you a little of my background, I was a career firefighter. Right now, I retired a few years ago and work with volunteer departments. So I've got over 35 years in the fire service. I trained to the level of a hazmat specialist. So I learned as much as I could about dealing with some of these high hazard fires that firefighters face on a daily basis. And when I retired, I was hoping, and I am learning to hopefully make our profession safer for firefighters as far as and industry by sharing and teaching, I should say, about encapsulator agent and trying to educate the difference between an encapsulator agent and foams and other agents that we're used to using that have been around for years and years and years. And we're finding as time goes on, they are less effective or seem to be less effective on some of our current fires that we face. So with that, I'd like to get the program started. We're going to be talking, like Hernan said, about our lithium-ion batteries, the hazards that we face on a growing basis. And again, I would like to welcome everybody, and hopefully we can get some good information out of there, some good questions, and move it as we go along. But just as a little bit on history on lithium-ion batteries, I mean, we know through history, as we've grown, we used to use the nickel metal hydride or nickel cadmium batteries, and they would develop memory, and they would, after so many charges, kind of fall by the wayside. And so technology has advanced, and we found that with this lithium-ion technology, we're able to store a lot of energy. And instead of that gradual drop off of the battery pack as it begins to lose its charge, with the lithium ion, they seem to hold that charge almost till they're out of energy, and then it's a rapid decrease. So they're a very, very efficient and effective source for being able to store energy. And when we sit there and we start looking at our concerns, you know, the demand continues to grow. We're looking at more and more vehicles, more and more accessories around our house. You know, instead of being plugged into the wall and using our electricity, we're trying to make everything battery powered. It seems like trying to get away from the plug-in type mode and just have to recharge. So the diversity of them is, you know, just constantly growing. The materials, but we also have to look at the multiple classes that we have to deal with when we start talking about some of the hazards. And we're going to talk about the toxicity when these batteries do fail and they start to burn, and we start getting those toxic gases that are being emitted, as well as flammable electrolytes. And then we talk about, and I mentioned the energy source. I mean, your lithium-ion batteries are an absolute great source of energy. But we need to look at all the aspects of it. It's not just the battery, but it's the case it's in. It's, you know, whatever the electrolytes, and what is the battery made up itself. And we know that these fires can start by short circuiting. I mean, the batteries are pretty much stable unless you have some kind of an impact or trauma. You drop them with vehicles, get involved in an accident. And then there's that, we want to have our phone back as fast as possible. So we get into that rapid charging, and, you know, we have heat that's generated when we start getting into the rapid charging, or we leave the phone up on our dash in our automobiles, in our cars, and we get overheat. So there's many things that can cause these batteries to overheat. And when they do, they go into what is known as thermal runaway. And the biggest concern with thermal runaway is being able to control and stop it, so that we can extinguish the fire. This is just a real quick news clip from
involving one of Tesla's cars with an autopilot feature. The car slammed into a tree and burst into flames. Police tell ABC News it appears no one was in the driver's seat.
Is that playing for you?
ABC's Gio Benitez.
Tonight, mystery surrounding it.
Yes, it's playing, Jeff, but the volume is a little bit low.
Okay.
Charred wreckage captured on camera after it crashed into a tree and burst into flames.
For some reason,
Two
it's
men
froze on
inside
me.
were killed. The Tesla's high-energy battery reigniting.
Yeah, I'm sorry. It's froze here too. It's
Okay.
volume is playing, but it was low.
8,000 gallons of water.
Next tonight to the deadly crash
There you
involving
go.
one of Tesla's cars with an autopilot feature. The car slammed into a tree and burst into flames. Police tell ABC News it appears no one was in the driver's seat. Here's ABC's Gio Benitez.
There's no tonight mystery surrounding a
This
deadly
is
crash
happened here
involving a
in
Tesla Model
U.S. It
S.
was in the Houston area,
Footage captured on
and I'm going to turn the
camera.
volume down, just kind of talk over. What ended up happening is there was two gentlemen in the vehicle, nobody supposedly in the driver's seat. The vehicle slammed into a tree and caught on fire. The fire department, believe it or not, used over what's reported 30,000 gallons of water to try to extinguish the fire. It appears that when we talk about these types of fires here in the U.S., they talk about the need for copious amounts of water. So I guess if you're looking for some type of a guideline for what is a copious amount of water, I mean, here, is an example where they used 30,000 gallons. They really still, from reports, never really got control of the fire. It pretty much burned itself out. They were only able to have a minimal impact on being able to cool these batteries. So when we sit there and start looking at all the hazards, the chemicals of the electrolyte and etc., what have we just done to our environment when we sit there and start looking at that much water being used to try to extinguish one car fire? It's a little ridiculous. And what I hope to do is give you a little bit of a better idea of how an encapsulator works. We're going to see, first off, I turned all those volumes down and they shot up on me. But this is just a real quick video showing how, no matter where we look, our dependence on lithium-ion batteries continues to grow. We're using them in our power tools at home. Those that use e-cigarettes, our automobiles, and along with the increased usage is the increased dangers, because if you followed the GM Bolt, we've seen multiple recalls. Here we have some engineers that were working on a robot. Luckily, they had gone to lunch before this unexpected failure. Again, when we start looking at some of our warehousing and some of our manufacturers trying to get away from the CO or the high-lows that are LP powered, getting to lithium ion. We've got an example here of how quickly encapsulator agent can work, and we're going to go over and we'll see some of these videos a little bit more as I continue on with the presentation, and I'll talk more about them. So when we sit there, we start looking about the popularity. I can't say enough. We're constantly looking and becoming more and more dependent on these, and they can be found in pretty much any place. I mean, you could probably in your chair look to your right or left and find an object or two that has lithium-ion batteries. In the energy storage systems, electronics, and we're going to see as we go through some of the others. But when we sit there and start talking, our hybrid vehicles and our electric vehicles, we need to think about those charging stations. Those charging stations are popping up all over. We're finding them in parking garages at our airports or shopping centers and parking lots. So we need to be aware of those. I mentioned the parking garages, our dealerships. How about the repair facilities, as we showed the one robot? But all the areas where these batteries can be, when we start talking about the automotive industry, need to be addressed. We're looking at just the vehicle, but I mean, what about where they're sold, where they're serviced, if they've been involved in an accident, where they're being repaired? These are all concerns that we're forgetting about. And I want to emphasize the towing companies, because again, when we sit there and start looking at these towing companies, if they're not aware of the hazards that these batteries can cause and that once they've been involved in an accident or some kind of a trauma, it could be hours to days later that they actually burst into flames. So if they park them too close to a structure or too close to other vehicles, and this is to basically fail and catch on fire, they can have a pretty large fire with all of the other vehicles around it. And as I said, as I travel around, I kind of try to take photos and pictures of some of the areas where some of these charging stations are popping up. And as you can see, there's no extra fire protection. We just put these charging stations in, and there's no thought behind what are we going to do to protect them. Here in the US, I mean, we have construction vehicles, our fire apparatus, basically anybody that is in maintenance and things like that carry their power tools. When we look at the aviation industry, we've got our unloading devices, our ground handling equipment. Again, we talk about those parking garages, the forklifts and some of the other equipment, our UPS backup systems and radars, as well as all the consumer electronics that pass through airports. Those are all a concern. And I bring up again, charging stations and our high-lows. We sit there and we put them in close proximity to each other, but there's no additional fire protection that we're adding or we're considering. And, it causes some concern because we sit there and we look at these fleet vehicles and how close they're parked together. And when we sit there and we start looking at how these batteries can react, as you can see, when one of them starts to fail, a violent reaction, you can see the amount of flame and fire that starts to be generated when these batteries begin to fail. It's rather impressive, to say the least, but at the same time, when I talk about that tow company, they have a vehicle that had been damaged by an auto accident too close to another building, or other autos, other cars that might be in their impound or in their yard. As you can see, these fires can be pretty aggressive, and as they burn, everything by them is going to sit there and it's going to start to burn as well. In a minute, we're going to see, like, watch the truck. As the heat continues to be put on it, the brakes fail. It rolls away. Now, depending on the incline, that vehicle will roll some distance, and now you've just passed your fire on to a larger, greater area. So again, you can make a small fire rather large when we sit there and we look at it. When we travel down the highways, yes, I mean, batteries are being shipped by truck. Here we have an example of a truck that caught on fire on the highway. And you can hear and see just how violently those batteries are when they start to go off. And one of the things I want to point out, and again, I'm not real familiar with exactly this particular incident, but in most cases, when batteries are shipped, they're not fully charged. So if those batteries being shipped are not fully charged, we're getting that type of a reaction from them. What do you think that would be like if they were fully charged? Just something to think about when you sit there and start looking at what's taking place here. This is a little airport support unit that kind of moves the planes around. Here it failed, lithium-ion batteries. Now you sit there and you're taking a support vehicle and you're destroying a multi-million-dollar aircraft, because we don't have the right solution. They're using what they've been taught, what they're aware of. They're using their dry powdered extinguishers. And you start to hear and see those batteries start popping. But again, we'll see some additional videos as I go through the program and hopefully give you a better understanding why powders don't work. As you can see, I mean, they're losing the battle when they sit there and they're trying to use the methods that they've always known. So I'll get into the consumer electronics as we go on through, and hey, we all have cell phones, laptop computers, our gaming consoles if we have kids, the power tools, hoverboards, and we know here a few years back when hoverboards were just coming out, all the fires because of the hoverboards failing, scooters and e-bikes. We hear about the hazards of some of those as we get more and more of these e-scooters within some of our cities to help people get around. They're renting them out, and our remote controlled toys for our kids, and battery backups for our computers. We're getting away from those lead acid or nickel metal hydride batteries, and we're using lithium ion. And when we sit there and we start looking at the configuration, these batteries come in all different sizes. I mean, they can be relatively small or large for the same tool, but if you sit there and you start paying attention, the batteries are rated on amp hours. So when we sit there and look at all the different variations of the tools I've listed up there in the top right, a lot of our fire departments for auto extrication, they're going to a battery powered tool. And as they sit there and again, they start putting these batteries on their apparatus, for the type of use that they're being used, cutting people out of vehicles and entrapment and things like that, those batteries can get some pretty good abuse. So again, making firefighters that are going and using these types of tools understand the hazards and to make sure that they are using the right or have the right extinguishing agent is critical. This is just a real quick video. Again, we're talking about one of those little e-scooters, just a little tiny pop. And you get to see just how violent just one of those little scooters can be. Now we sit there and we go over here to our laptop computer. And you can see plugged in, overcharging, just how violent these batteries can fail from overcharging or just from a short circuit. Not bad. The laptop could have been dropped, could have been damaged in some way, and being plugged in and unattended can pose a hazard. And we have one of our it appears that they've tried using some agents to extinguish it with no luck. Continues to reignite, difficult to extinguish. We also have to understand is, again, we're dealing with thermal runaway. There's also multiple makeups of the batteries, and we'll cover some of those makeups of the batteries as well. And I know our power companies, this is probably one of our biggest and fastest growing areas where we can show some concern as we sit there and we try to become less and less dependent on fossil fuels, and we start looking at ways to store energy. We look at, for instance, the Tesla battery walls. We look at industrial storage. They call it power shaving. What they'll do is they'll make these large boxes or Connex boxes, or sometimes even actual buildings, and they put hundreds and hundreds of lithium-ion batteries as a storage system. So what they do is during the peak hours when the cost for energy is at its highest, when the demand is the highest, to help meet the demand, they use these lithium-ion battery storage systems to help feed the grid. And then later on at night when the demand lessens, they recharge these mass storage units. And as you can see, they're growing in use all over I know here in the US where we have wind or solar, like, they're putting in some of these storage systems to, again, what we call do that power shaving. So we sit there, we start looking at some of the examples and some of the different things that have happened. On January 19th, we have an aircraft evacuated because of a burning mobile battery. A boat, persons injured, an aircraft again. Arizona, one of those energy storage systems that I was just talking about, had an explosion that injured 4 firefighters, 2 career ending. So the hazards and with these batteries and not knowing how to deal with them is very important. And hopefully, as we go through and continue on in the program, I'll give you a better idea of how and why encapsulator agents work. But when we look at our medical industry, all the different uses, again, I can't stress enough as to how our dependence and our growth of all lithium-ion batteries and all of these different industries and all of these different parts of our life are just constantly growing. And as far as our navigation centers. So we get back, we saw a brief video of this. Again, the high-low, just kind of going through, doesn't appear to have any type of a damage to it. It all just without any notice, without any indication that it's going to fail, it fails. Now, as we're going to see in most of our structures, our fire codes are very clear that we need to have an ABC type extinguisher. So they are going to go throughout their warehouse here. They're going to start grabbing their ABC extinguishers and they're going to make an attack on this lithium-ion battery powered high-low. Appears that they're having some success. They might have it under control, or it's looking pretty good for them. But again, I caution, we're not doing anything to cool these batteries. And as you can see, because we're not able to cool the batteries, the dry powders are very, very useless. Again, when we look at some of the hazards, battery powered bus, when it's in a terminal, now we have the not only the bus that's involved, but as well, we got a building and a structure. So the question I ask now is, are you prepared? Are you ready to deal with these types of hazards that you could be faced with when you start looking at the growing uses of lithium-ion batteries? So let's look at the effectiveness of a dry chemical. As you just saw in the video with the high-low, the dry chemical was ineffective. It did nothing to help us cool the battery. Can't prevent the reignition. Doesn't do anything as far as removing the toxins that are being released when these batteries burn. So it's very ineffective. It doesn't help us to be able to extinguish these types of fires. Now, these are some videos. Again, I'm going to show, this is with dry powder. It's showing that there's 182 lithium-ion batteries that are the 18650 makeup. Shows that they're 95% charged. And as we sit there and we go through and we start making our attack with the dry powder, it's ineffective. It's not being done. Now, these are tests that were done through third-party testing with our Europe office and the Johnson Controls. And as you can see, you can pile the powder up and pile the powder up, but you're doing nothing to cool. You're doing nothing to be able to stop that thermal runaway. So these powders are absolutely ineffective when trying to use them on this type of a fire. Go to the next one. There you go. So the next thing I want to talk about is foam, because in the fire service, and as many of you may know, if you're having type of fire background, the things that we've in the fire service is known are water and foam. So if we use water and water doesn't seem to work, the next best thing is go to foam. And we're going to, again, I'm going to point out a video how I'll show the ineffectiveness of foam to be able to remove the heat, because foam creates a blanket. What do we do at night when we get cold? Pull up a blanket. So same effect with foam. We're not doing anything to remove the heat. As far as the reignition, the foam retains the heat, so it doesn't help us. It doesn't do anything as far as the toxins being able to be removed from the burning batteries, and it does nothing to encapsulate or to have an effect on the toxicity of the electrolytes. So what we're going to do is I'm going to show this video with the foam. Again, it's the same makeup. It's 182 of the 18650 cells. Again, this was with third-party testing with our European office, HCT Europe, and Johnson Controls. As you see, the attack with the foam is doing absolutely nothing to get any type of a control on these lithium-ion batteries as they start to burn. It cannot stop the thermal runaway, so therefore you continue to have that violent reaction. Also, the toxic HF gas that's being released, it's doing nothing to encapsulate or to reduce those amounts of excuse me, of toxins that are being released into the air. The next one that's probably very common, we see these in a lot of our data centers and things like that, are inerting gases. Inerting gases are efficient as far as being able to smother a fire and maybe inert the oxygen, or take the oxygen out and create a smothering effect, but they do little to nothing as far as cooling, very little, and therefore they don't stop thermal runaway again. The reignition, and I will say, when I mentioned earlier that explosion in Arizona with that battery energy storage system that injured the 4 firefighters, the fire protection system in that storage container was an inerting gas. So it once the container was opened, oxygen was able to enter into that container. All the things needed were still there because the inerting gases did nothing to cool, nothing to remove those toxic vapors and those flammable gases. When the oxygen was there, they had an explosion again that injured those. So these inerting gases are very ineffective as well. So I'll show this. This is one where they're using, again, inerting type gas. They're using CO. Our CO2, they're going to come in. You'll see the engineers that were just recently working on them were luckily gone to lunch when this occurred. So we need to start to think about what's taking place here. Here we have a person making a valiant effort to try to extinguish. He does not have any type of air pack on, any type of a breathing apparatus. Cooling effect is not there. He is not able to cool the batteries to a point where they don't reignite. But look at how much of the gas is being released into the room, what he's breathing in, and the hazards he's putting himself in. The firefighters are going to come in here shortly and they're going to open it up and pull it outside. So very ineffective as well. So we saw the video at the very beginning. I started it with the Tesla, and it was water. And as we sit there and we start reading a lot of reports here, and I'm not sure about other countries, but the choice is water, and it's copious amounts of water. And throughout my fire career, when I hear copious amounts of water, it kind of sets up flags because I have no guidelines. And And now we have a case where 30,000 gallons. A normal car fire throughout my career, 500 to 800 gallons, I can put a car fire out. Now I'm getting into the area. So if this was a Tesla and it was going down the highway in an area where there was no readily available water supply, what do you do to try to mitigate this without causing damage to your infrastructure? Because as you can see how violently these batteries burn, just think of what they can do to a roadway as far as causing damage. So when we sit there and talk about copious amounts of water, again, causes me some uneasy, some red flags go up. The reignition, we again find that through reading and knowing about the hazards of lithium-ion, when they have been put out with water, again, days to weeks later, they have been known to reignite after being extinguished with water. Water does nothing to remove the toxins, not only the HF gas, but also in the electrolytes. So that copious amount of water, where's it going to run off to? What kind of environmental damage are we causing? I mean, in the past, when we started talking about our foams, we look at the fluorine. Now, if we're using foams and other agents, as well as copious amounts of water, where is it going? Again, 30,000 gallons of water on one vehicle, and it's still, from the reports that were given, it burned itself out. They truly never extinguished it. They would put it out, it would reignite. 30,000 gallons of water and ended up pretty much getting towed away. So when we sit there, we start looking at, the damage, the overcharging. Batteries do have safety systems built into them. However, when they start getting involved in accidents, the safety systems can be damaged or have some type of a impact to them that causes them to fail as well. So they go into their thermal runaway. We look at temperatures above that 800 degrees C. So we need strong cooling to be able to control that thermal runaway. So when we look at the results here, the significant hydrofluoric acid emissions, one of the things that I want to point out is the gentleman that was trying valiantly to put that fire out. He was breathing in all that HF gas, and I would imagine it was well below some limits of exposure without having some type of a health effect. So now let's talk and understand how encapsulator agent F500 is a better solution when we talk about some of these high hazards. When we look at other agents, we look at our foams, we have to be considerate of our fluorine, the PFOS and the PFOAs, the forever chemicals as they're called. And when we start looking at some of the fluorine-free foams, again, they're very ineffective at being able to deal with this. F500 has been tested. It is 100% fluorine-free. It's non-corrosive. It's 100% biodegradable. It's a multi-class AB suppression agent and a combustible flammable liquid vapor and spill control agent. When I do a lot of my trainings, I ask
encapsulator
foam
technology
that you're aware of that is a vapor control agent. So when we sit there and start looking and I start talking about encapsulator agent, the first thing we need to have an understanding of is
the
what
next generation
it
of
is.
fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic nonpolar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with the nonpolar tails inward and the polar heads outward, forming millions of spherical micelles.
I want to pause it here for a second because this is probably the most critical point and part of the program. If you understand the molecule and how it forms these micelles, you have a better grasp of how the agent works and being able to cool and extinguish and stop thermal runaway. Pause it too long. So
Encapsulator tech. Once
when we
the
sit
EA
there and we look at
molecules
it,
enter the water, they instantaneously and automatically orient with the nonpolar tails inward and the polar heads outward, forming millions of spherical micelles. Micelles travel towards and exit the nozzles, forming EA droplets. Micelles nearest to the surface of each droplet automatically break apart. The nonpolar tails orient outside the droplet with polar heads on the surface, forming an EA skin on the surface of every droplet. In addition to the EA skin, there are millions of molecular spherical micelles within each droplet.
okay, I'm going to pause it here again, because as you can see, instead of making bubbles, we're chemically changing the makeup of a water droplet. And by changing that, we're changing the characteristics of how it's able to cool and extinguish. That skin, all those tails on the surface, they rapidly absorb the heat, drive it inside to those spherical micelles that are inside the water droplet. Those spherical micelles in the droplet, they rapidly absorb that heat and then slowly release it into the water that's around them. And in doing so, they do not create steam. So we are able to cool and be able to do these things without causing a superheated atmosphere. Again, you need to really understand the molecule to understand the how it works with the polar head and the nonpolar tail. That polar head loves water, nonpolar tail fears water, wants to get away from it. So as water droplets come out of our nozzles, our sprinkler systems, whatever type of system that we're using to get the agent out onto a fire, as it comes out of the nozzles, it's going to come out into the air. Again, those molecules on the surface, they're going to split out. Tails are going to come up, spin out to the surface, and we're putting a skin on the surface of each and every water droplet and changing that characteristics on how it's able to cool and extinguish. And as long as you can understand that versus a bubble, a foam structure, or a thin wall bubble structure that's fragile and cannot encapsulate or cool, you have a pretty good understanding of how and why an encapsulator agent is able to work. So we're going to talk now and get into a little bit more on the encapsulation and how it works with lithium-ion batteries, because it does work on many classes of fires, not just the lithium-ion. So the independent tests have shown, that, the cooling ability of F500 can stop thermal runaway. The main thing that is the biggest thing that we hear every time people talk about lithium-ion battery fires, it's that thermal runaway seems to come up. Well, here we have a way to stop thermal runaway, and we can do it rapidly and quickly. And here's just an example of a cell, and we'll see this cell a little bit further into the program. You see the batteries that are over here on the right, they've gone into thermal runaway. They had failure. They started burning. F500 was applied to this battery, and as you can see where the arrows are pointing to, those are batteries that, because we were able to stop the thermal runaway, those batteries were not damaged. One of the most hazardous aspects of these batteries is the hydrofluoric acid, the gases, the hydrofluoric vapors. They're toxic, and we will see as we move on just how toxic they are and what type of an effect an encapsulator agent can have. So when we sat there, we talked about water and the copious amounts of water being able to try to stop the fires. Now we're looking at an encapsulator agent that's able to rapidly cool these batteries, able to stop that thermal runaway, greatly reducing the amount of water you're going to need. Not only does it help stop the thermal runaway, but now we're sitting here, we're looking at the flammable electrolytes. We're able to encapsulate those flammable electrolytes, rendering them non-flammable, non-ignitable. So we're reducing and we're actually changing those in making those, if by chance they are to get involved in some water runoff, we're able to have a change to that makeup of those electrolytes. As far as the toxins, the HF gas, and the things that we're dealing with, we're able to have an effect on that as well. We're able to reduce the toxins that you'd be exposed to. So we've been proven to be a highly effective, powerful, fast agent on being able to stop these batteries from burning with much less water and being much more effective. So here we have a comparative test. And again, it gets back into the videos I showed earlier, where we were using the powder, the foam, and the F500. This was, again, testing that was done in conjunction with HET Europe and Johnson Controls. They're testing their agents, as you can see, as they use the F500 on the battery. He's using just like short little squirts. He's not using constant, and he's having a great effect using very little agent on the battery, being able to stop that battery, being able to stop that thermal runoff. I will say, when we sit there and we start talking about the HF gas, and I would like to point out that the gentleman, you see him appear every once in a while, that he was not wearing an air pack, and because of that, he spent some days in the hospital detoxing. And the reason I want to bring that up is because as we go through and we start looking at the results from these Kiwa tests and the Johnson Control test on the batteries, when they tested the powders, they came to the results that powders do not work on lithium-ion batteries, don't apply. When they started in testing the foams, they gave them moderate to poor, but again, recommendation was not to apply on a lithium-ion battery fire. It's really not very beneficial. But the F500 and all the tests that they ran, sufficient and can be used on these lithium-ion battery fires. So the conclusion is that encapsulator agents are very effective agents, that are able to stop that thermal runaway better than your foams. And as we saw in that last slide, we can use it on our lithium-ion batteries very efficiently and very effectively. This is a video while we were looking at the 18650 cells earlier. This is an example of a polymer pouch style battery that you might find in a tablet or some of our other electronics, such as scooters or other areas where we need to make a difference. Some of our automobiles, not all, use 18650 technology. Some of our automobiles, some of the manufacturers are using polymer pouch style batteries. But as you can see, when an F500 agent is applied, that rapid cooling effect, even on that polymer pouch battery, the encapsulation of the vapors. This one's another good one to show. I like to show it because as you see this polymer pouch battery start to fail, those nozzles for the fire suppression are pointed towards the top, the plastic housing. So when the battery fails, it's basically overspray of putting this. And you can see just how quickly the agent is able to encapsulate the electrolyte, the HF gases, and extinguish this battery by being able to stop the thermal runaway that's taking place and being able to cool that. This is testing that was done. This is a relatively long video, so I'm going to kind of speed through it. Things that I would like you to pay attention to is up in the top right. You'll see there's thermal imaging. On the bottom right, they have multiple sensors, heat sensors. And if you will pay attention, I'll point out some of the temperatures as we go along. They're working to put this battery into thermal overload. And you'll see some heat in that top image with the thermal imaging starting to show some heat development. As I progress through, we'll see in the top left, we're starting to get some smoke that's being generated, some HF gas being released. Our temperatures are starting to rise, but not a lot as of yet. Starting to see a little bit more smoke come off here with the battery. A little too much. So we're getting ready. And as you can see, when these batteries again fail, there is a very violent reaction. When the one battery that fails generates enough heat, then the battery next to it fails, and it's just a constant chain reaction until all of these batteries fail. Again, I'm going to kind of speed this up a little bit. I'm now going to ask you to watch the thermal imaging and the temperatures as they continue to rise. Starting to see some 400 degrees C's. You look up here, we got some really good heat on our thermal imaging camera. The temperatures are continuing to climb. On our number 5, you'll see how quickly those temperatures are starting to rise. I like to use the number 5 sensor because as you can see, and I'm going to back it up because we were just at 5, 6, 700 degrees C, and watch how quickly when F500 is discharged, those temperatures drop. So I went from 500 degrees, and I'm down now to 17 degrees C in just a matter of seconds, with just that quick burst of encapsulator agent and being able to stop the thermal runaway and encapsulate the batteries. Now, this is the battery that you saw that showed the damage to the left and then the non-affected cells. Some of the other things that they were looking at as we progress and look at it, I'm going to move ahead now and talk about that HF gas that we've been discussing and pointing out throughout this presentation. We started talking about at lithium-ion and F500. When we looked at water without extinguishing the batteries, and we look at the parts per million, and when we looked at the parts per million on a 18650 cell, and then the polymer pouches, we're looking at about 227 to roughly 2,600 parts per million. When they sat there and they used an encapsulator agent to extinguish these batteries, we were able to drop those parts per million from 227 on those 18650 cells to anywhere from 1.8 to 1.25 parts per million. And when we started looking at the polymer pouches, where we were at 2,600, now we're down to 37 to 19. So it's a huge difference when we sit there and we start talking about lithium-ion batteries. Again, let's go back to that warehouse, or let's go back to some of these other areas where that robot was being worked on. And if people are in there and we're using an F500 extinguisher, and we're able to knock those parts per million down that much, okay, well, look at, I mean, you're looking at somewhere probably right around a 20-minute exposure without having health effects, or, that could be long lasting. It gives you, let's say, a little bit of a safety margin. Get yourself evacuated when you're sitting there and you're looking at F500. So when we sit there and start looking at the solutions, I mentioned again, we look at these charging areas where the high-lows are. We look at fleet buses. We look at all the other areas where we may have a large quantity of lithium-ion batteries. And we can sit there and we can use what we call concentrate control systems, or our like water-driven proportioners. And they can service multiple risers in multiple areas within a facility, protecting charging stations throughout an area, throughout a facility. And we're in good company. Look, I mean, we have many companies that are using our product very effectively to be able to control the hazards that lithium-ion battery brings. So I kind of want to show again, this is one I'm going to give Hernan credit for. This one he shared with me. This was a lithium-ion powered fire truck. I want to see if I can turn the volume up on this. It is a little bit because it's pretty impressive. Again, you know, here we have pretty good blast. So when we saw that truck on the highway, I mentioned that, you know, they go down the highway with about a 30% charge. There you saw the results of something that had a full charge, something that had a little bit more of a charge. So, you know, comes the question, you know, it's time for us to wake up. Okay, it's time for us to wake up and find and start to use the solution. And in ending, I want to show there's no advance notice when these are going to fail. So that the hazards that are generated as we sit there and we go through dealing with these types of batteries and all of their applications, as you can see, they can fail without any notice at any time. So with that, I will open it up and see if there are any questions.
I have a question for Mike, please. Mike, I know we've, in Europe, you equipped, I believe in Germany, a bunch of quick response vehicles with TKO nozzles and F500 just for this kind of problems that they were having. Has that been a successful exercise?
Graham, what we've showed here today are just some of the more recent testing that's been done. Starting with the Kiwa testing in the Netherlands. And then because the gentleman who did all the fire extinguisher testing actually got transported to the hospital, every testing since that has been sprinkler testing at the university level, highly documented, highly instrumented, backed by a PhD person at that particular university. And I don't know if people notice, but those tests at the university levels are done in conjunction with Hazard Control Technologies Europe and Johnson Control. So if you don't know who Johnson Control is, they're about a $35 billion a year company. They're the largest single supplier of fire protection in the world. They own Tyco, Warmold, Simplex, Grinnell, Ansel, ChemGuard. And the reason they're teamed up with F500 is even though they're the largest foam and dry powder fire extinguisher provider in the world, they've come to realize that those technologies don't work. And F500 has gained a huge reputation in Germany based on testing that goes back as far as 2008 with Bosch. So Bosch was making lithium-ion batteries. They had warehouse storage and they were seeking for a solution. So they studied foam, wetting agents, water, F500 encapsulator agent, and they standardized throughout their entire facilities worldwide on the F500 encapsulator agent. They then shared those results with the local. They're in Stuttgart, and so that is the Baden-Württemberg state, and they shared all of their findings with the German fire school there at Baden-Württemberg. And so in Germany, they actually have an SOG for hybrid electric vehicles. They shall apply F500. So every fire truck in Germany has at least one F500 encapsulator agent, turbo knockdown and overhaul nozzle. So I don't know, maybe Jeff, if you can search and see if you can bring up a picture of that. But basically it's a 75 liter per minute nozzle. So that's 20 GPM, has a 2 liter bottle that you put the F500 concentrate in. It hooks up to a standard 1.5 or 1 inch hose, and they're using that to fight every electrical car fire and now every flammable liquid car fire in Germany. So when I heard Jeff say his experience is, let me see, the last Tesla where they used plain water in Texas was 30,000 gallons. I call that copious amounts of water. That's 30,000 gallons of runoff. That's 30,000 gallons of hydrofluoric acid running into your streams, killing your fish. And then I heard him say that, typically his fire department through his 30-year career would use about 500 gallons. And I was like, Jeff, are you kidding me? We're putting car fires out here with encapsulator agent somewhere between 20 and 100 gallons. So that's what Germany has settled on. And I know when we started introducing the TKO nozzle into the United States, the fire departments were looking at us kind of cross-eyed. They were like, whoa, I'm gonna go fight a car fire with the 20 GPM nozzle? Are you guys nuts? And we're like, no. And then we were demonstrating it and they go, holy crap, Batman, this stuff is amazing. So yeah, we're really changing the complexion of firefighting. And we've had a real run-in with foam. HCT manufactures a Class A foam that's fluorine free. We were for a short period of time in the Class B foam business. Thank you, Hernan. I guess that's bringing up TKO nozzle so you can see what it looks like. So basically you have the 2 liter bottle. Whoops. You hook up, you can get it with Stort's coupling, British instantaneous coupling. So you get your nozzle supply, your encapsulator agent, and it gets proportioned right there at the nozzle. Hernan, can you kind of point to the dial on the 75 liter per minute? You can dial up 0.5%, 1%, or 3% on that dial and a flushing. The beautiful thing about that is after you've extinguished the car fire, you disconnect the hose, you have 0 wasted agent because there's nothing but water all the way up to the nozzle. So it's a nice little device. It's handy. We're now doing car fires with anywhere from 20 to 100 gallons. There's no runoff. And here in the US, we're pretty conscious now because there are multi-jurisdictional lawsuits going on where cities, municipalities, states have joined together to actually sue a lot of manufacturers, mainly DuPont, 3M, even Johnson Controls, Ansel, Tyco, those guys for all the fluorinated pollution in the United States. And so when you look at the encapsulator agent, since we're not relying on bubbles, we have no fluorine. And so it's an ideal agent that's not polluting the environment. So there's a big awareness and a lot of fire departments are starting to say, why are we laying down foam and 500 gallons of a foam solution when we can put a fire out with 50 gallons of an encapsulator agent solution? So we're starting to see this TKO nozzle take off within our fire service here as well as in Germany. Did I answer your question, Graham? Kind of long-winded. So here you'll see, if you see the little stuff on the ground, that was just to make sure we were actually flowing agent. You see that little small puddle to the right. But after we're done extinguishing a car fire here, there's less runoff from that car fire extinguishment than we had just to check if the nozzle's charged.
All right. You absolutely answered the question, Mike. I mean, I can't think of any more efficient and economic way to handle something as frightening as a car fire can be. I mean, it's just there's nothing else on the market, really.
Well, I just came back from Reno, Nevada. I spent 3 days at Tesla's Gigafactory. We have currently 15 systems in place at the Gigafactory. I met with the head of fire protection construction for Tesla, and they are now moving the F500 encapsulator technology to their Fremont, California plant, and they're building a brand new, will probably be about 5 million square feet under roof in Texas. And so we were talking about fire protection of the lithium-ion battery charging stations, and they were showing us their new, the 18650, they now have a 21650 cell. They were showing us how our agent is being used to protect the formation room, where they actually heat the batteries up so that they can get a film between the anode and the cathode sides of the battery. So we'll be going out there August 9th to commission GC8, which is one of their lithium-ion battery charging stations. So yeah, some of the testing that Jeff showed in Kiwa, that was actually a result of Tesla in Europe said, we need a fire extinguisher, but we need a third-party certification. And so if you look at the Kiwa report, you'll see that there's like a Westgard name on there. I don't have the report up in front of me, but that's actually a fire extinguisher distributor of Novapene, and Novapene is a division of Johnson Control. So that's why the testing took place in the Netherlands. It was Tesla who was demanding that in Europe. And so Novapene, being a division of Johnson Controls, asked Johnson Controls if they could test F500, and Johnson Controls Europe said, well, I don't know. We need to check with Johnson Controls in the US at headquarters. So they contacted JCI in the US because you're now asking to test a competitor's product. So JCI in the US said, yes, you can test F500 EA, but you have to test all of the fire extinguishers that Ansel makes and all of the products that ChemGuard makes. So there was actually 3 days of testing. HCT Europe was invited to day one, and that's some of the video you see, the dry powder, the foam, and the F500 encapsulator agent. We were not invited to day 2 or day 3, where they tested every other product in their arsenal. But I can tell you on day 4, they contacted HCT Europe asking if we could do a joint venture together with Johnson Controls to make an F500 fire extinguisher for lithium-ion batteries. So, and to me, I believe Johnson Control, being a $35 billion a year company and the largest supplier in the world, you know, I can't get better credibility than that when they come and ask us to joint venture with them for fire extinguishers. And, you know, when we sat at the meeting together, they said we have two possibilities. One, turning our customers like Volkswagen and BMW over to HCT because we don't have a solution, or partner with you guys because you do have the solution. So we have partnered together, and we not only are doing the fire extinguishers, but we're also doing some fixed systems together using the HCT diamond doser water-driven proportioners.
Mike, can I share my screen to show how were the TKO and the temperature, how down so fast?
Sure. I guess if people want to see, I'm game.
Yes. Sorry. Okay, you have 1200 centigrade here. See, this is a TKO. See how fast down low from 1000 to 200.
Yeah, very quick.
Yes, and you don't use a lot of water. You don't use a lot of time. The firefighter is not on racing the speedway, and you has control of the fire in seconds. Okay.
I was doing a in-service training with a regional group out of Minnesota, and they had a car to burn, and they thought they were going to pull a big surprise on us, and they had a magnesium steering column. And so we were using the TKO nozzle and very quickly knocked everything down, and then hit the steering column. And you could see, oh, okay, this has some magnesium in it, but we were able to get the steering column extinguished, the magnesium cold, all in about 35 seconds. And the fire departments were like, holy cow, I can't believe this. We thought for sure, and wait a minute, why, when you hit the steering column with about a 20-degree fog pattern, we did not see the big mag flash, the explosions that you see with water? Why is that? And I said, do you remember when we were in the classroom and did the training, we talked about the spherical micelles, and the ones that are closest to the surface break apart and form the skin on the surface of the droplet. So when the F500 droplet is coming on to the magnesium steering column, it's no longer H2O coming in contact with the magnesium. It's actually the F500 molecule that's coming in contact. You remember when I said, think of the water droplet like an orange, where the peel of the orange is the F500, the pulp of the orange that you would eat is like the H2O water molecules, and the seeds of the orange are the spherical micelles inside. So when you hit that steering column, it was the F500 molecule that's coming in contact with the magnesium, and we don't have any hydrogen and oxygen in that molecule. And two, we rapidly transfer the heat into the internal portion of that droplet and around the spherical micelles. And they said, well, we could see that. We had a highly like 3,600, 4,000 degree burning magnesium that you just took down to 200 like that. So glad to say that they've come aboard.
Yes. This is something about what you were talking about. Can you see the flames when it starts?
Yes, yeah.
See how it starts to download here.
Yeah, see the flame goes out and we're not touching the flame. Ah, why is that? Oh, think about the fire tetrahedron. Heat is one of the forgotten leg of the fire tetrahedron. Get rid of the heat, you get rid of the fire. Bring the heat down below the auto ignition temperature. So in the lithium ion battery, you can use copious amounts of water, but you get no benefit for the off-gassing of the HF off gas. You can reduce the temperature, but it's going to return again, and you have exposed electrolyte that's a flammable liquid. So basically, you have a flammable liquid along with increased temperature, you get and the oxygen, you get reignition. What are we doing? First, we're changing that heat reduction mechanism of the droplet to more rapidly reduce the heat than plain water. But secondly, we're encapsulating the flammable electrolyte inside those spherical micelles. So we are separating the fuel from the oxygen on a chemical molecular level. And when you see how those batteries will explode, there's no way to mechanically put a foam blanket over and keep it on there. Boy, the explosions just blows the foam all over the place. So, but we're doing it on a chemical molecular level and rapidly reducing the heat. So, we're actually interfacing with all four legs of the fire tetrahedron.
Yeah. Thank you, Mike. We have a question. I believe this is for you or Jeff.
Yeah.
Stephen Shee, can you open your microphone and make the question?
Mr. Stephen Shee, how are you?
I'm good, thank you, Mike. Thank you so much for the presentation. We have a question. After we mix the F500 into extinguishers, how long or say how often we need to replace our agent?
Okay, we have actually run a study and we have an ongoing study. We have mixed up 1, 3, and 6% agent, and we have done that with fresh water, distilled water,
Sure.
fresh water that we've taken from the tap, and local lake water. And we initially were testing it on a monthly basis until we got the year 2, and now we're doing it every 6 months, and we're 3 years into it. So and it's been satisfactory. We haven't seen any diminishment of the percentage of the agent there, which we're using refractometers to determine, hey, this is 1%, this is 3%, and this is 6%. We're not seeing any biodegradability. The agent is 100% biodegradable, which is my major concern as to, geez, if we put this agent inside a fire extinguisher, is it going to actually biodegrade? Of course, why I initiated the test. So we're 3 years in. The agent has not biodegraded, which then my light bulb goes on and says, the testing we have done says our agent is 100% biodegradable when in the presence of activated sludge, which is the microorganisms that you find in a wastewater treatment plants all over the world. So we're not putting any activated sludge inside the fire extinguisher, so we're not biodegrading the agent. So right now we will document 3 years, but it's an ongoing study. So come January, we may update that to 4 years.
I can verify the 3 years. I had extinguishers in my vehicle, and I actually used them on magnesium.
Right.
They were 3 years old and worked very well on the magnesium.
Awesome. Awesome.
And I know like the NFPA codes require, NFPA 10 requires like a hydrostatic test after 5 years. And And there's some other requirements for foam fire extinguishers to
That's correct. Yes.
place the solution after maybe a year. Here's what we're talking about. Even the F5, take a 9-liter fire extinguisher, and you make a 3% fire extinguisher. It's 270 milliliters. It's a quarter of a liter. Even if you're buying it at $20 a liter, which is not what we're selling it at, but a quarter of a liter at $20 a liter is $5 of agent. I mean, you want to risk life safety for $5? I mean, that's
100%. Yeah.
about if you were to change the solution out after 3 years or even every year. So we recommend just kind of at this point, follow the Nfpa codes, which would be a shorter period than the 3 that I mentioned.
Awesome. Thank you, Mike.
You're welcome.
Thank you, Mike.
You're welcome.
Yeah.
By the way, that forklift fire we show, that they are now a customer of ours because what you don't see in that video is after they discharged 9 ABC fire extinguishers, so those were ABC dry powders, and they couldn't put it out. They kind of vacated the warehouse, but no one had put the brakes on the forklift, so it rolled down the aisleway till it finally crashed into the rack storage. The total loss, $250 million. And so we got introduced to that particular client by their loss control. It was an Excel Global, and the vice president of Excel Global introduced me to that customer and introduced the F500 encapsulator agent to us. And so now they've outfitted every place they have those type of batteries with the F500 fire extinguishers and with what we call QAMUs, which are quick attack mobile units. So we have a 25 liter, 50 liter, 75 liter, and 100 liter QAMUs. And so usually at their charging stations, they have a bigger 100 liter QAMU, and then they have the 2.5 gallon or the 50, 25 liters placed throughout the facilities. And we're talking about a major company here, one that operates in all 50 states of the United States. And I don't want to say the name here, but that's a lot of loss over a fire extinguisher. And right now I can also share that Ron is not on here. Jeff Monkowski is our Western area manager. And Jeff, nice presentation. Thank you very much. And Ron is our Eastern area manager, and we have met with FDNY. They're using our agent for 3-dimensional Class B flammable liquids. We first got introduced to them, I would say back in 1999. I filled out a 70-page application on encapsulator technology and submitted it to the R&D section. To this day, I can't tell you whatever happened to that application, and neither can FDNY, but they had a transformer fire. FDNY Hazmat has been using encapsulator agent for flammable liquid spill control in New York City since about 2003. They come to realize that, geez, when we have a gasoline spill in downtown Manhattan, we can just encapsulate it with the F500. It renders it non-flammable, non-ignitable, and non-explosive. And then we can just let it evaporate right off the pavement. We don't have kitty litter. We don't have absorbent pads. We're not paying transportation. We're not hauling it to a hazardous waste site where at the hazardous waste site, it evaporates off into the atmosphere. So we're saving all this cost by doing in situ encapsulation. So anyways, we have a transformer fire that's taken place in Queens. They come out and pump about 1,500 pounds of purple K onto the transformer, and excuse my language, but just kind of pissed off the fire. And then they decided they're going to do a foam operation. So they set up and applied AFFF foam for an hour. The foam, of course, we have a three-dimensional transformer that's on fire. And as we all know, foam works by creating bubbles, forming a blanket to separate the fuel from the oxygen. Well, the foam would go to the top of the transformer where the fire was, would run off the side of the transformer. So we can't mechanically maintain the separation of the fuel from the oxygen. So the foam is running down and goes into the Bronx River, results in a $6 million fine to the power utility. Well, at that point, Hazmat shows up on site, and Hazmat, who's been using F500, talks to the suppression guys and said, why don't you try this? So they gave them a pail of F500. They put an inline ejector in, dialed it up to 3%, and put the transformer out in a minute and a half. And it was cool to the touch. And the foam chief, a guy named Steven Sanfilippo, turned to Hazmat, Lieutenant Cassidy, and said, holy crap, what kind of foam is this? And Cassidy said, it's not a foam, it's a newer encapsulator technology. So we did get invited to come to FDNY, present to all the top chiefs. And I asked the chief, I said, you know, about 18 years ago, I filled out this 70-page application. Does anyone know where that was? He goes, don't worry about that. You guys are way beyond that stage now. He goes, I really understand now why the dry powder didn't work, why the foam doesn't work, and why your agent does. You have the ability with these spherical micelles to encapsulate fuel, whether they're in a vapor phase or whether they're in a liquid phase. So technically you can smother a three-dimensional fire. You can smother in a three-dimensional environment. And I said, yes, exactly. And don't forget cooling. Get rid of the heat, get rid of the fire. Provide the burn back resistance by getting the temperature below the auto ignition temperature of the fuel. So Hernan now has up on the screen, he's showing an article from FDNY. This gets circulated to about 80,000 firefighters in the US. There's 3 different articles. Hey, can you slide up until we can see Sanfilippo? This is Lieutenant Cassidy on the top. Whoops, sorry. This is their foam manager, Steven Sanfilippo. Here he's writing the article just over on the left side. It's pretty small, but he talks about F500 and how they're using it. And within FDNY, he talks about this incident and how successful it was. And Hernan, can you slide up just to the top of this gray area, the box we're in right here? At the very top of the second column, he talks about the encapsulator technology having a myriad of applications, including Class D, and that they're using it on that type of materials. Since then, we've met with them talking about lithium-ion battery. And so now they're moving forward with implementation of encapsulator technology for lithium-ion battery. And one of the questions I posed to them was, NFPA 10 here requires ABC dry powder fire extinguishers about every 75 feet in commercial buildings. And I know that the ABC fire extinguisher can put out a 40B flammable liquid fire. So that would be 100 square feet, which is 10 feet by 10 feet. So I asked the operations chief, I said, let me ask you, how many 10-foot by 10-foot flammable liquid pits do you guys have on the 50th floor of the Empire State Building. How many big flammable liquid hazards do you have there? And he said, 0. I said, how many lithium-ion battery hazards do you have on the 50th floor of the Empire State Building? And he said, yes, there are every cell phone, every iPad, every laptop, even some of the computer servers now. And so, yeah, we're moving forward with New York, and they're putting forth their own SOGs and codes based on encapsulator technology. Yeah, this is their SOG, or suggested operating guideline for use on transformers. If we scroll down to section 4, we can see a little bit further up. No, up. Just above the table. Here we go. Right here. Stop. Go down a little bit. Keep going. See here, as we look, we see section 4.3 where they talk about in October 2010, the F500 produced the desired result. So moving forward, they're using F500 encapsulator agent. And the table just shows the various standoff distance that they would apply different devices. So if they're attacking a 345,000 kilovolt transformer using a 30-degree fog pattern, they have to stand back 25 feet. And if it's other streams, they have to stand back 125 feet. And knowing in the US that a hose lay is actually 50 feet, they're now use their hose to measure the distance they are from the transformer, either a half a hose, or in the case of 125, 2.5 hoses. And that's how they mark off the distance in the field in order to make sure they're standing back far enough that they can apply the encapsulator agent solution without the leakage current coming back to the nozzle. So it's an exciting new technology. And, you know, I can remember UL did a test, and they showed that the time to flashover in a standard living room back in the 60s took about 30 minutes to get the flashover. But now we move forward and we have different materials, polypropylenes, polyethylenes. And so now in a standard living room, in a house, the time to flashover is 4.5 minutes. And so the question becomes, you know, if the fire department takes 3 to 4 minutes to respond, now you got 30 seconds before you're in a flashover situation. And if you're using plain water, are you actually bringing a knife to a gunfight? So you know, due to Nfpa codes, you know, we know the frequency of fire is much less. But due to the modern materials, the severity of every fire is much greater. And with this encapsulator agent, we know that we can come into an interior attack. We can Z the ceiling with a 20-degree fog pattern, and we instantaneously drop this heat temperature from where the flashover is almost occurring down to like a warm, moist shower almost instantaneously without the creation of superheated steam. Secondly, we know we encapsulate the unburnt carbons, so we're removing the flashover fuel that causes the flashover in the first place. So we're addressing the fuel at the ceiling, we're addressing the heat very rapidly, and we're encapsulating things like benzene, dioxin, toxins that are really causing the cancer in the firefighters. So you have a huge knockdown advantage, but you have huge huge safety and health benefits to the firefighter. So here you can see what's happening. 3 minutes and 40 seconds today versus, back in the olden days of the 1960s, takes 30 minutes. One of the things that we are definitely experiencing in the United States is fire departments would purchase foam hoping they would never have to use it. And if we think about it, and we make foam, it's just I can't get any of my guys to sell it. It's just very limited in its scope. It's if you have a nice confined flammable liquid where you can put a blanket on top to mechanically separate the fuel from the oxygen, it's great application. But what our customers are saying is, we used to buy foam hoping never have to use it. Well, if the chief's house was on fire, we might pull out foam. We actually buy encapsulator agent because it solves everyday problems. It's so versatile and it has so many health and safety benefits that we can't afford not to use it.
Thank you, Mary. Like you were talking about the difference between the modern days and the old days. We have a video that we have run on Maumee, Ohio, to see how fast you can use in a structural fire.
Yeah, this is an interior structure, 0.5%. So here they're using like a laser pyrometer.
Yes, a thermal camera.
Huh?
They are using a thermal camera.
Okay. And so if I recall, the temperature gets up to about 12 or 1300 degrees. And then they come in through a hallway and apply the agent. Well, I said the hallway, now I see they're putting it in here at 0.5%. You can see the black smoke turning to white. Here, the guy's standing in this vapor, but it's not steam. He even said to his chief, "Oh, I was standing right in the steam and I didn't get burned." And then the chief said, "Well, it's not steam. Steam is at 100 degrees C, and what you were experiencing is something around 32, 33 C. It's like, I can't even call it a hot sauna bath. It's more like a warm, moist shower." This is the one later in the evening, right?
In the night, they burn again.
Yeah, I think if I remember this was later in the night. They were getting, again, the thermal imaging camera. One of the things they were seeing was the temperature was hotter near the top. Down at the bottom where they had pulled out the pallets and put new pallets, they put some on top of the ones they had burned earlier in the morning, and they did not reignite. So they were like, "Holy cow, look, the temperature at the floor is really low." And it was because those pallets would not reignite.
Okay.
That might be a video. We can hyperlink to the YouTube or Vimeo channel so that when Hernan's going to send out the recording to this meeting, the presentation to the meeting, and maybe send a few hyperlinks to our online services for some of those so they can hear the sound now they got a little
No.
background.
Mike, we have another question to you. Is John, do you want to make the question?
John,
Maybe.
if you're going to retrofit a sprinkler system with the F500 encapsulating agent, do you have to use a special kind of sprinkler head for the dropper?
Okay, that's a good question. And the answer is that you have to have 100% coverage of the hazard. So for example, let's say it's a flammable liquid tank and we're using foam chambers and we're sticking foam down just at certain points on the tank and we're expecting the bubbles to float across the surface. You not take just the foam out of the tank and put F500 in. It works differently. So in that flammable liquid tank, we would have to have a redesign to have a full coverage. Let's say you're in a rubber tire facility and you have a sprinkler system in there, and that sprinkler system is designed for the 100% coverage of that particular hazard. In that case, you can actually cut into the main riser pipe, put an atmospheric tank, plumb in an HCT F500 diamond doser proportioning system, and proportion the F500 directly into that system. So that's not a problem to do. We use open head deluge. In fact, a lot of the transformer fire protection that we do, there's already an existing water system there, and it's designed like a bird cage all around the transformer to spray water. Philosophy there is to let's cool this transformer until the local fire department, who's usually a volunteer fire department here in the US, because we build our plants away from the public, so they're out in the middle of nowhere. We want to just use the sprinkler system to cool that transformer to prevent the spread to other transformers until the local guys can show up and pour thousands of gallons of foam on, creating a $2 million environmental cleanup. Okay, now we've been approached by multiple companies and do these where the system's already in place. They're saying we want to add F500 here for 15 minutes and provide 15 minutes of reserve. So we're going to do 30 minutes. So let's say that sprinkler system, the water demand, just for simplistic purposes, was 100 gallons per minute. That was the water demand. So you just multiply that times 30 minutes times 3%. That gives you the quantity of agent you need. And then we just plumb into that. Actually, the fire protection contractor does it. We'll provide the atmospheric tank. We provide the water-driven proportioners. We provide the agent. We provide the connections between the tank and the water-driven proportioner. The contractor installs all that, and then we come out and do a commissioning and certification service. So we'll pump the agent into the tank. We get everything set up, make sure all valves are in the right way, and then we'll run a proportioning test and confirm that if it calls for 3%, we're actually flowing at a 3%. So we probably have 150 or more jobs in the US like that for transformers. This is a particular nozzle that we like, and it works very good. We had a project in the Grand Cayman Islands. It was Caribbean Utilities Company, and they had a foam system in place. And when they had the fire, they have big, huge diesel engines that they use to generate the electricity. Well, a diesel engine is a big three-dimensional block. It's like a transformer. Well, the foam discharge just flowed right off the top of the diesel engines. It couldn't maintain a separation from the fuel, from the oxygen. They ended up with 2 deaths and a huge loss. And so their insurance company, can you stop that there? So their insurance company was familiar with the encapsulator agent's three-dimensional Class B fire capabilities. And so on that project, there's 3 separate phases. We've completed phase 1, which is engine rooms 5 and 6. And I think it resulted in like an 1,800 gallon F500 bladder tank. Will proportion into 6 different risers and feeds into these nozzles. We call these nozzles VEEP nozzles, vapor encapsulation explosion prevention, or sometimes we refer to them as rotating nozzles. Now, the reason we say VEEP is, I think if Hernan goes forward just a little bit, maybe to the 108 second mark, okay, right there, stop right there. Don't do anything yet. So here we have a fire. This is LNG gas. This is coming out through the piping, and you can see the piping is about 1 meter off the ground. So if I was going to try to put a foam blanket over top of this, I'm not going to be successful. I cannot mechanically separate the fuel from the oxygen. So here we're going to spray using those rotating nozzles, the ones I call VEEP, V-E-E-P nozzles. And Hernan, I just want you to go forward just and a little, stop. I want you to click the play and then just till it starts and then until the nozzles start, and then unclick it and stop it again. Stop. Oh, okay, well, you missed the spot I was looking for, but you could see right there, you got it right there. Stop. Oh. I want you to see part of the fire out and part of the fire going. It's hard to get there. Okay, it's hard to get there because it gets extinguished so fast. But what we're doing is we're encapsulating the fuel inside the spherical micelle while we simultaneously cool below the auto ignition temperature. So when I saw this video, I said, oh, wait a minute. Why do we even need to wait for the fire? We have equipment that can detect a flammable liquid vapor leak called LEL meters, PLDs. We can detect that. So what we're going to see is maybe we have a pump seal or at a pump station along a pipeline, and that seal starts to wear out. Now we get flammable liquid leaking out. Now we get vapors coming off of that. Those vapors go until they find a hot spot in the refinery, maybe a steam pipe. We have a major explosion that kills a bunch of people, causes millions, if not billions of dollars of property damage. And when I see this video, I go, oh, hang on. We have a technology to introduce to the world a whole new application. Why wait for the explosion? We can encapsulate those vapors, hence vapor encapsulation explosion prevention. Detect the vapors, encapsulate the vapors, prevent the explosion, prevent the fire, prevent all the attorneys from chasing the ambulance and running into the refinery looking for anybody they can to sue, the big oil companies and the insurance companies. I'm thinking to myself, wow, who's not going to be on board with this? Prevent the fire, prevent the explosion. Everything needed to do that exists except the spherical micelle, which is our technology that we created. So we're in the process of patenting VEEP system, this very application here. And, you know, the components will be the same. You know, you'll have nozzles, you'll have fire pump, you'll have water-driven proportioner, you'll have encapsulator agent, you'll have a detection system, you'll have a panel that sends a signal to the operator to shut down zone 1 or 2. It'll also send the signal to the fire pump to turn on to start encapsulating the vapor. The only thing that's going to change is the size of the projects. Is it something on a pump seal, or is it something where we're surrounding a distillation column? You know, just what are we doing? But it was this video here that we did out in Utah that made me think of the VEEP application. And moving forward, one of the things that was missing was the code to govern that. And coming out in October of 2021 is the code that will cover vapor encapsulation explosion prevention systems. And that code will be NFPA 18A. Yes, sir.
What you've just described is exactly what we're going to need for the hydrogen cell power buzz that we're hearing right now. I mean, that's something that's really taking off, but you've just really just described something that we need to control that, because hydrogen would be phenomenally dangerous otherwise. VEEP is brilliant.
Yeah, I mean, this will encapsulate and stop that. So, and again, you see in there is an encapsulator technology, the spherical micelle, literally smothering that fire, separating the fuel from the oxygen in a three-dimensional volumetric area. Not unlike foam, that's a two-dimensional, you know, put it over top of the surface area. We're encapsulating stuff that's 1 meter off the ground. And it doesn't need to be on fire to encapsulate it. So that's going to be a whole new application that I'm proud that our company is going to bring to the marketplace. I'm sharing my screen here. I'm on NFPA's website, and I actually sit on 3 different technical committees. I do not sit on this one. This is NFPA 855, but 855 is a standard for installation of stationary energy storage systems. And because their systems are really so new, and we're talking about copious amounts of water, that's what the NFPA has come up with. The technical committee is, you know, really trying to find different applications. So you see 6.1 is sprinklers. They're talking about spray systems. Just want to scroll on down here till we get to, yeah, 6.5 encapsulation reserved. So here, this information here about encapsulator technology suppression systems, and it talks about lithium-ion battery and the many hazards, and you know, this water additive of encapsulator agent conforms to this section 18A, section 7.7, talks about the testing. Kiwa, Dacra, Daimler, Chrysler, General Motors, Panasonic, Tesla, Bosch, Fraunhofer University, TU Clausthal. As I said, we got a ton of testing that's been done. And then it goes in to talk about the basic building block of encapsulator agent as a spherical micelle. And the qualification test protocol for micelles are NFPA 18A, section 7.7. And it goes and talks about that and the 3 major things the micelle does. One is the encapsulation, and the second is the rapid heat reduction, interruption of free radical. and how all three of those things play into the suppression of lithium-ion battery, the statements. Here's overviews of the testing. So all of this stuff is going to be put in the standard, including design, different types of systems like we do sprinklers, water spray, water mist, pre-engineer hybrid systems. We're currently doing a system for 2 containers going into Westar Energy. So it's a pre-engineered self-contained system where we're using nitrogen gas to drive the solution in the nozzles that are inside the racks to protect. So, you know, the things we're talking about here today are not just, well, you know, we like the agent and we think it's the best thing out there. The bottom line is it's going to be an 18A standard referencing lithium-ion battery. It's in the 855 standard. And you just don't get these things in NFPA standards unless you have a big, huge plethora of testing to support putting these type of things in. So this is a real technology. It's here to stay. And, you know, I encourage you that you didn't learn everything you know about foam in 1 2-hour meeting. You're certainly not going to learn everything about an encapsulator agent in a 2-hour meeting. So I encourage you to continue to liaison with our people in Australia, with Graham Higgs at EHM and John with Fire Striker. And I think Baden was on here at one time, Baden Davies. And, you know, continue to ask the questions, get the information, because this is a real technology, fluorine clean, environmentally friendly, and it's good for multiple applications. Those are my simple comments. I love you, everybody.
Thank you so much, Mike.
God bless. God bless. You guys have a great day. And that's all I'm going to say.
Again, I want to thank everybody for sharing their morning or afternoon with us and trying to learn more about encapsulator agent technology, how it's different than foam, how it transforms the fire service, and how we can look at some of these more difficult fires. I know I concentrated more on the lithium ion. Mike covered the other wide applications and uses of F500 encapsulator agent and everyday uses in the fire service. And I shouldn't just say the fire service. I mean, we're looking at industrial applications and fixed fire protection systems. I mean, I'm constantly awed by the applications and the designs that we're being asked to create and to the new industries that we're being, I guess, brought into to provide fire protection systems, because it's such a versatile agent. It can do so many different things, and the cooling abilities. And I mean, as I said, when I retired from the fire service, my goal was to use my knowledge and training to make the profession safer. And all of that led me to hazard control technologies as the solution. And I mean, once you understand the difference between a thin wall bubble structure and the chemical change of a water molecule using encapsulator agent, the differences and the applications are just phenomenal, and how much less water you need to be able to extinguish these difficult fires that foam is not designed to. And when Mike started talking about the 3-dimensional fires, go to NFPA 11, the foam standard, and that Annex A11, it states foam will not work on a 3-dimensional fire. But yet in the fire service, what do we know? Water and foam. Okay, so I go about and use my, I guess, training, or rather than trying to do sales pitches, I go in to train them on the difference between foam and encapsulator agent, and you make the decision on what you feel is best for yourselves and your community.
Bye.